Hello and welcome to Lecture 5 of the Principle of Relativity in Phys 1104. And in this lecture we're going to look at convertible kinetic energy, which is not the kinetic energy that a car has when it's got its roof down. Let's look at three very similar situations. Here we have identical cars about to crash into each other, and I've set it up so that there are three different situations with their velocities. So in situation 1, car B is stationary and car A is coming at it at 30 meters per second. In situation 2, cars A and B are coming at each other, each going at 15 meters per second, although that means there's a relative speed between them of 30 meters per second. And in situation 3, they are going in the same direction, one at 20 meters per second and the other at 10 meters per second. Which of these is the most dangerous situation? I mean, they're all going to result in a crash. And let's say that all of the collisions are totally inelastic so that the cars stick together at the end, and so we can just talk about a final velocity in each case. And if you work through the totally inelastic collision, you come up with those values that I've listed on the screen there. What's going to happen is that kinetic energy is going to be converted into internal energy during this inelastic collision. And that is where the danger is, because that internal energy represents damage to the cars and the people in them, possibly. So it seems reasonable that the collision with the most kinetic energy should be the one that is the most dangerous. If you look at the kinetic energies of these three situations, this is what you come up with. You can calculate this yourself fairly easily. And this would suggest that situation 1 is the most dangerous, 3 is the second most dangerous, and 2 is the least dangerous. But if you think about that, that doesn't make much sense. In situations 1 and 2, the relative speeds, which intuitively ought to be the thing that really matters, are the same. And in situation 3, the relative speed is much smaller. It's only 10 meters per second. So we would intuitively think situations 1 and 2 would be the most dangerous and would be about equally dangerous. And situation 3 would be perhaps much less dangerous. If that's what you intuitively think, you're right. And to see it, you just have to look at the final kinetic energies. And note that the change in the kinetic energy in situations 1 and 2 is the same, but that there's only a very small change in the kinetic energy in situation 3. So the kinetic energy alone, the initial kinetic energy, was sort of misleading. One thing to realize is that situation 2 is in fact exactly the same as situation 1, but viewed from the center of mass frame. And it's the simplest situation, particularly because the final kinetic energy is 0. So that suggests it may always be productive to think about collisions from the center of mass frame when we're trying to decide how much kinetic energy can get converted into internal energy. Last lecture, we saw how we can transform the momentum from any arbitrary frame into the zero momentum frame, and we found that that gave us some useful relations. So now we're going to do the same thing with the kinetic energy. In other words, we're going to establish a relationship between the kinetic energy as measured in any arbitrary reference frame with what the kinetic energy would be as measured from the zero momentum frame. And again, we're going to find this relationship useful. The full derivation is long and involves a lot of kind of icky algebra, so I'm going to leave it for the supplementary video. If you want, you can look at that to see how the derivation goes, or even better, try the derivation yourself and then compare it with the supplementary video. What I'm going to do here is just quickly summarize what that derivation looks like. So we start with the kinetic energy for our system as measured in our arbitrary frame A. And now we do a Galilean transform on all of these velocity components. Now, because these velocity components are squared, that means this whole thing expands out into a rather icky relationship. But what I've done in this equation is I've grouped the terms in a very specific way. And what you can see is that this middle term contains a sum of all the momentums. But it is the system momentum as measured in the zero momentum frame. And so by definition, it's zero, and that whole term goes away. In the first term, you can see that we have the total inertia of the system, and then everything that's left here at the end is what we were actually looking for, the kinetic energy of the whole system as measured in the zero momentum frame. And so here is our relationship between the kinetic energy as measured in the zero momentum frame and the kinetic energy as measured in any arbitrary frame. Let's just spend a little bit of time looking at this relationship and thinking about the meaning of the quantities in it. If you look at this first term, you see that it's a half mv squared. It's of that form, and so it's a kinetic energy, and specifically it's the kinetic energy of some imaginary object which has an inertia equal to the inertia of the whole system, and it's moving at the center of mass velocity of the system. And so this often gets called the kinetic energy of the center of mass. And notice that it really only involves motion of the system relative to the observer, right? This velocity component here is to do with how the zero momentum frame moves relative to the observer. On the other hand, this last term is all the other motion of the system. In other words, the relative motion of the objects in the system. So this gives us several important things to take away. This kinetic energy of the center of mass is going to be different for every observer, because every observer in general is moving at a different velocity relative to the center of mass. And we've seen already in an earlier video lecture that the center of mass for an isolated system moves at a constant velocity. And so we expect that for isolated systems, this kinetic energy of the center of mass doesn't change. On the other hand, all observers will always agree on this kinetic energy that's the internal kinetic energy as measured from the zero momentum frame. This will be changed by internal interactions, because internal interactions change the relative velocities of the particles in the system. And so this is the part of the kinetic energy that can be exchanged back and forth with the internal energy of the system, or it can be converted. And so it often gets called the convertible kinetic energy. Let's just take one more look at this in a special case that's useful. So in a system of two particles, you can show, although it's difficult and involves math you haven't seen, that that convertible kinetic energy can be written in this form, where this funny simple symbol mu here is called the reduced mass, and it's written this way. And this v12 just refers to the relative speed of the two particles in the system. So notice now that this is something you can actually calculate quite easily without bothering to transform into the center of mass frame, because you can always calculate the reduced mass, and the relative speed of the two particles is something that all observers agree on, no matter what reference frame they're in. So now we can return to our three situations with the cars and see how we could have got our answer very easily using these expressions. So first of all, the reduced mass is the same in all three cases because it's the same pair of cars, and so it is just note the units. The kilograms take out the kilograms, but there's still 1 kilogram left in the numerator, and this one comes out to 500 kilograms. Notice it's smaller than the mass of either car. There's a reason this is called the reduced mass. Now that we know that, we can easily get the convertible kinetic energy. Notice that In situation 2, we have the same reduced mass and the same relative speed, and so we will get exactly the same answer, in line with our expectations about the level of danger of those two collisions. Whereas in 3, we get quite a different answer. If you look back at the beginning of the video where I did this, you will see that the amount of kinetic energy that was converted to internal was only 2.5 times 10 to the 4 joules for this one, instead of 2.25 times 10 to the 5 joules for these two. I'm going to finish up by returning to this problem that we looked at in the last lecture. Now, hopefully I didn't traumatize you too badly with how nasty the algebra got when we looked at this problem before. Let's look at it again and use these new methods that we've just seen. So it's still going to be useful that in the zero momentum frame we can write our conservation of momentum this way. Or we can rewrite that as and that allows us, as before, to eliminate one variable and write it in terms of the other. Now, the key realization we have here is that the kinetic energy of the center of mass does not change between the beginning and the end. And so all that has to happen is whatever initial convertible kinetic energy we have, plus the spring energy, that has to get converted into the final convertible kinetic energy. And this gives us an easier way of finding our way to a solution. So here's what we can do. We can realize that the relative speed is given this way, which we can now use this to replace this is now useful because we can just rewrite all of this in terms of the convertible kinetic energy. So our final convertible kinetic energy is just a half mu VAB final squared, or in other words, where I've dropped the absolute value because it's being squared, and that equals our initial convertible kinetic energy, which we could have easily calculated, plus the spring energy, which we were given. And so note that the only unknown here is this, and so we can solve for that, transform back into our original frame, and so on. And so this gives us a much quicker solution than we had in the last video lecture, although it involved some rather difficult insights about the invariance of relative speeds and about being able to ignore the center of mass kinetic energy.